Cycling. Cycling refers to the end of inspiration. It determines the length of inspiration. BCT is the sum of Ti and Te. If BCT is given, an increase in Ti causes a corresponding decrease in Te, and vice versa. Time cycling and flow cycling are commonly used cycling mechanisms. Time cycling. With time cycling, you can define Ti in several ways, including Ti, I/E ratio and peak flow. Time cycling by setting Ti. In this case, an operator directly sets Ti in seconds. The ventilator switches from inspiration to expiration when the set Ti is over. This method applies to both volume and pressure breaths. Time cycling by setting I/E ratio. Every breath cycle time or BCT has two portions, Ti and Te. The ratio between Ti and Te is I/E ratio. The number on the left of colon represents the Ti portion and the number on the right the Te portion. Assume that we set the rate to 10 breaths per minute for a BCT of 6 seconds. If the set I/E ratio to 1:2, the resulting Ti is 2 seconds, and Te 4 seconds, respectively. The advantages of I/E ratio are, A. A change in either I/E ratio or the set rate causes corresponding changes in both Ti and Te, and B. The relation between Ti and Te is clearly shown. The disadvantage is that you do not get Ti and Te in second without mental calculation. Note, in an active patient, the actual breath cycle time, Ti and Te may differ from the expected values. The I/E ratio method applies to both volume and pressure breaths. Time cycling by setting peak flow. It is a bit confusing. How can Ti be defined by setting peak flow? Peak flow refers to peak inspiratory flow. This method applies only to volume breaths with a square flow pattern, meaning that a ventilator delivers the gas at a constant flow rate during inspiration. Under this condition, Vt is the product of Ti and peak flow. Therefore, Ti increases when you increase the set tidal volume or decrease the set peak flow, or both. Ti decreases when you do the opposite. Flow cycling. Flow cycling is another way to terminate inspiration based on the change in inspiratory flow. It is designed for active patients and is the key property of support breaths that we will discuss later. In a pressure breath, the inspiratory flow is uncontrolled. Typically, the inspiratory flow rises quickly to the peak at beginning and then drops gradually back to zero. Flow cycling works with the descending part of the inspiratory flow. The peak inspiratory flow is taken as 100% regardless of its absolute value. A ventilator switches from inspiration to expiration if the inspiratory flow drops to a preset level in percent. If the flow cycling is adjustable in your ventilator, you can find the control of flow cycling. In all Hamilton medical ventilators, this control is labeled as expiratory trigger sensitivity, ETS. You can set it anywhere between 5% and 80%. This control is unavailable if flow cycling is fixed at factory. Flow cycling enables you to influence the Ti of spontaneous breaths. The lower the set percent, the longer the Ti is, and vice versa. Flow cycling is very useful to improve patient ventilator synchrony. Flow cycling can fail if the system has a massive leak and the ETS is set very low, because the inspiratory flow cannot fall to the set cycling level. The consequence is endless inspiration. This is clinically unacceptable. To avoid this possible incidence, a ventilator has a backup time cycling, which may be adjustable. If so, you can find a control for that. In Hamilton medical ventilators, this control is called maximal inspiratory time or Ti maximum.